Hello, everyone. I would like to tell you about our paper titled Gadget Structures in Proofs of the Kochen-Specker Theorem. My name is Ravi. I work at the University of Hong Kong, and this is joint work with Monika Rosicka, Stefano Pironio, Carol Mihal, and Pavel Horodecki. And all of them except Stefano are at the University of Gdańsk, and Stefano Pironio is from the University Libre de Brussels. So this paper is published in Quantum this year. So a quick motivation for what we did. So essentially, we are working on the Kochen-Specker theorem, which you may know. So a brief recap is that the Kochen-Specker theorem states that it's impossible to find a deterministic, non-contextual assignment to measurement outcomes on quantum systems for Hilbert spaces of dimensions greater than 2. And the traditional way to prove the Kochen-Specker theorem is to consider a set of vectors S, which has some finite set of vectors in CD. And the question is whether we can have an assignment F that maps every vector in this set to a number that is either 0 or 1. Now, this assignment must obey the following two conditions, which are known as the Kochen-Specker conditions. And they essentially state that if we have a set of mutually orthogonal vectors, then the sum of the value assignments must be less than or equal to 1. While if you have a complete basis, so if you have some set of vectors that form a complete basis in this dimension D, then the sum of the value assignments must be equal to 1. So one way to prove that it's impossible to have a deterministic assignment is to simply exhibit a finite set of vectors that does not admit such an assignment, which is also known as a 0-1 coloring. Now, in the study of the Kochen-Specker theorem, it's usual also to consider what are known as orthogonality graphs. These are graphs in which we represent each vector in the finite set by a vertex of the graph, and we connect two vertices by an edge if the two vectors are orthogonal. So we can translate the 0-1 coloring from the vectors to the 0-1 coloring on the vertices of the graph. And the translation is that the assignment must now assign to the vertices of the graph the value 0 or 1 in such a way that for every click of the graph, the sum of the value assignments must be less than or equal to 1, while for a maximum click in the graph, the sum of the value assignments must be equal to 1. So another way to state the Kochen-Specker theorem is to say that there are finite orthogonality graphs or finite vector sets such that their orthogonality graphs are not 0-1 colorable. So in particular, we are interested in constructing proofs of the Kochen-Specker theorem, minimal proofs of the Kochen-Specker theorem, and other points in relation to these proofs. And one of the more interesting points is the feature known as 0-1 gadgets or bugs in this substructures in these proofs, substructures in these Kochen-Specker sets of vectors or subgraphs in these orthogonality graphs. So one such famous substructure is this one, which is known as the Clifton bug, which is a set of 8 vectors that live in dimension 3, and the orthogonality graph is shown here. The interesting point about this structure is that if we start to assign values 0 and 1 to the vertices in this graph, or alternatively to the vectors in this structure, then no matter how we assign it, as long as we obey the Kochen-Specker rules, we can never assign both U1 and U8 the value 1. So one way to see that is that if I assign U1 and U8 the value 1 in this value assignment, then by the Kochen-Specker rules, U6, U7, U2, and U3 must all be assigned the value 0 because they're all orthogonal to either U1 or U8. And then the rule that in every maximum click we must have a 1 states that in U4 must be assigned a value 1. And similarly, U5 must be assigned a value 1, And this in turn contradicts the fact that we are assigning values 1 to two vertices that are adjacent, or alternatively to two vectors that are orthogonal. So the crucial point is that there are these two vectors, u1 and u8, that are not on their own orthogonal. So the Kochen-Specker rules themselves do not forbid you from assigning any values to u1 and u8. But the structure of the graph is such that you cannot assign values 1 to both of these, meaning that if you do, then the Kochen-Specker rules lead you to a contradiction. So what we can do is to define a general graph or a general set of vectors with such a property. And this is what we do. So we say, suppose I define a 0, 1 gadget to be such a set of vectors that is on its own 0, 1 colorable, except that there are two distinguished vectors v1 and v2 that, despite being non-orthogonal, cannot both be assigned the value 1 in any Kochen-Specker 0, 1 coloring. Now, what is the point of the study of these gadgets? And this is the first main result that we show in this paper. We show that for any Kochen-Specker graph, meaning any orthogonality graph that shows as a proof of the Kochen-Specker theorem, there is always inside this Kochen-Specker graph, always such a 0, 1 gadget as a substructure. And moreover, given such a substructure, given such a 0, 1 gadget, by using many copies of this and connecting them, we can always produce a proof of the Kochen-Specker theorem. So this is a very general statement that says, irrespective of whatever graph you show me, as long as you state that this is a proof of the Kochen-Specker theorem, then the statement is that there is always a subgraph inside it that is a 0, 1 gadget, meaning that in this subgraph, there are these two vertices that are not adjacent on their own, but you cannot assign values 1 to both of them. So what is the point of that? Is that we have the study of minimal proofs of the Kochen-Specker theorem and minimal orthogonality graphs, meaning the graphs with fewest vertices and edges that provide us proofs of the Kochen-Specker theorem. And this theorem essentially says, this result essentially says that instead of studying minimal proofs of the Kochen-Specker theorem, it may also be quite useful to study minimal 0, 1 gadgets. Meaning, because these 0, 1 gadgets are even smaller than the proofs of the Kochen-Specker theorem, it's almost as good, almost good enough to study the minimal 0, 1 gadgets, because they capture the essential contradiction that is in the Kochen-Specker proof, right? So essentially, they're kind of equivalent, that if you have a Kochen-Specker graph, you can look at the subgraph, and the subgraph already captures the essential contradiction that is needed to prove the Kochen-Specker theorem. So there is this 0, 1 gadgets play kind of a defining role in proofs of the Kochen-Specker theorem. And so the question is, given any two vectors, even if they're non-orthogonal, can you find some other set of vectors that put together with these two form a gadget? And of course, the constructions are given. There are many detailed constructions that we show of 0, 1 gadgets for different any two given vectors in any Hilbert space dimension in this paper. And for example, one candidate solution for any two distinct non-orthogonal vectors is given here, which is a 0, 1 gadget between these two vectors, u1 and u42, and they are parameterized in some particular way, depending upon the overlap between these two vectors. Now, this is one example. There is an interesting question: what is the minimal size of these 0, 1 gadgets? Because as I said, in the study of Kochen-Specker proofs, there is a large area of the literature is devoted to finding minimal proofs of the Kochen-Specker theorem for different Hilbert space dimensions. In particular, there are records known set by Perez and Cabello and others on minimal proofs of the Kochen-Specker theorem, So our idea is to look at the substructures and to find minimal such substructures. And there are a number of other results that we give in connection to the Kochen-Specker theorem in 0-1 gadgets. In particular, we show that the 0-1 gadgets can also provide what are known as statistical proofs of the Kochen-Specker theorem. These are proofs that do not rely on 0-1 colorability, but directly look at a state-independent non-contextuality inequality. And a famous such result is a result by U and O that was in PRL in 2012 that provides a statistical proof of the Kochen-Specker theorem, even though the set of vectors that is given is a 0-1 colorable set. So never mind what exactly that is, the idea is that we get constructions of other types of statistical proofs that can be provided starting from 0-1 gadgets, and some of these results that are stated in the paper. Furthermore, we even prove an extension of the Kochen-Specker theorem using this notion of the 0-1 gadgets. So there is an idea to show an extension of the Kochen-Specker theorem. So what is the extension that we are interested in? So remember that in the Kochen-Specker theorem, we are assigning values 0 and 1 to the set of vectors in our finite set. So in general, you can consider arbitrary assignments in the interval from 0 to 1 to the vertices of the graph or to the vectors in the set that obey the Kochen-Specker rule. Now, obviously, the Born rule itself is a valid probability assignment to the vectors. So the extension of the Kochen-Specker theorem asks for a 0-1 assignment, an assignment in the interval from 0 to 1, such that there are these two distinguished vectors that if you insist that both of these two vectors be assigned values in either 0 or 1, then it's only possible if both of these are assigned values 0. So this is an extension of the Kochen-Specker theorem that is related to the Gleason theorem, and this was considered first by Pitowski in the Journal of Mathematical Physics in '98. And he gives a complicated proof, and we show that by looking at 0-1 gadgets and particular extensions of those, we can actually give very simplified proofs of this extension of the Kochen-Specker theorem. Now, this extension of the Kochen-Specker theorem also has connections to the generation of randomness based on contextuality. So quantum random number generation, where we certify the randomness based on the violation of a non-contextuality inequality. Now, I will not go into the details of the explicit protocols that you can get based on these gadgets. Nevertheless, I want to state that these gadgets kind of, through a connection to what are called Hardy paradoxes in non-locality, allows us to simplify the proofs of many device-independent protocols on randomness amplification, in particular this paper from PRL in 2016. So there are a number of constructions of such 0-1 gadgets that allow us to simplify these proofs. And as a foundational result, the 0-1 gadget construction allows us to improve what's called the Hardy probability in Hardy paradoxes. So if you know something about Hardy paradoxes, then you may know that an interesting question there is, what is the maximum value of the Hardy probability? So in the original Hardy paradox by Hardy from PRL from a long time ago, the value of the Hardy probability was 0.09. And this was improved to up to value of 1/2. So there is a question of what is the maximum allowed Hardy probability. So what is the maximum value of this Hardy probability? And we show by means of these constructions that are given in detail in the paper that you can actually increase the value of the Hardy probability, not only to 1/2, but you can actually go all the way to 1. Okay, so this actually completely solves this open question which was open for a very long time in the field of Hardy paradoxes. So it's very interesting that there is this connection not only to the Kochen-Specker theorem, but also to Hardy paradoxes in non-locality. So I don't have time to go into all the technical details, so I will just conclude by saying that in this paper, we say that the Kochen-Specker proofs that we are kind of very much interested in for many reasons. In many settings, it's sufficient to consider these smaller structures than the Kochen-Specker proofs that we call zero and gadgets, that are also called bugs or other types of names in the literature. And so in many applications to do with contextuality, or even in foundational results to do with contextuality, it may be worthwhile to restrict ourselves to zero and gadgets, okay? And to try to find minimal constructions of zero and gadgets, and to find minimal proofs of the extension of the Kochen-Specker theorem, and to identify the role of zero and gadgets in randomness generation, certified randomness amplification, and so on. And in particular, to use these to provide simpler proofs of randomness generation protocols. So with that, I direct your attention to the paper in Quantum from this year, wherein a number of more details are explicitly laid out. So with that, I thank you for your attention. Let me stop here.